All right, ladies and gentlemen, if I didn't get a chance, say good afternoon as you walked in. Good afternoon. I hope all is well. I'm here to talk to you about section 11.3 today, which is multivariable systems. This is one of the last sections that we have to do when it comes to systems. So we've talked about solving systems, solving nonlinear systems. So the last one we have is multivariable systems, which is exactly what it sounds like. It has multiple variables. We've seen a lot with two variables, x and y, that you solve with substitution or elimination. So for multivariable systems, the only difference is that there are three variables instead of two. So the first thing to know is a three-variable linear system would look something like this. There are three possibilities for solutions. So when you go back to what we did with substitution elimination for just two variables, we know that there was either one solution, no solution, or infinitely many solutions. So it turns out that the same exact idea happens here in three variables. You could have the case where there's a single solution and something in three dimensions actually represents a plane. So if you look over here on the left side, you'll see a green plane, you'll see a pink plane, you'll see a blue one. So if all three planes intersect, notice that they intersect at a single point. If they intersect at a single point, that means that there is a single solution for that system. How about these three planes in the middle? We'll notice that two of the planes will intersect at a time, but there are no places where all three planes intersect each other at the same time, so therefore there would be no solution. In the last one, notice there are three planes. They intersect along a line, so in that case, that line goes on forever, so there would be infinitely many solutions. So the kicker here is that very similar to what we did in two variables, there are three possibilities for solutions. So let's do a couple examples. They'll give you a nice idea of how this looks. Again, it's not a super long section here at the end, but definitely some good examples. So example number one, can we solve the following system by using back substitution? So in this case, it wants us to do it with substitution. And what it means by back substitution is just plugging in what you know, what you're starting with, plugging back into other equations to figure out what those are as well. So I always like to do it by listing the equations kind of in order. So our first one, of course, is going to be number one. This one's going to be number two. And the last one's going to be number three. That way, when I start doing my solution, I'll reference them by number. So that way, if you're looking at them, you'll know that the first one is the top one. The second one is the one in the middle. And the last one is number three. Okay, so in two variable systems, we wanted to find out what the solutions were for x and y. So for three variable systems, we actually want to find out what the solutions are for x, y, and z. So notice in this case, we're just trying to find one more variable. So the first thing that I notice is looking at equation 3. Equation number 3 is telling me that z is equal to 4, which means that I already have part of my solution. I know what z is. Z is going to be 4. So that's kind of nice. It doesn't always happen that way. I would say that that's a nice case for something that happens. But now what I can do is I can take what I know about z equals 4 and I can back substitute it into one of the other equations. So would it make more sense to plug it into equation number 1 or plug it into equation number 2? I would say plug it into equation number 2. Notice in equation 2, there are y's, there are z's, but there are no x's. So in this case, if I know what z is, I could actually substitute it into equation number 2 and then I could solve for y, because y is the only other variable. So I'm going to start with equation number 2. I know that y plus 2z is equal to 6. But I know something now about z, so I can say y plus 2. And then for z, I'll plug in 4. And I know that this is equal to 6. I know that 2 times 4 is 8. Again, the whole thing's still equal to 6. Subtract 8 from both sides. Y is equal to negative 2. So now notice I have another piece of the puzzle. I want to try to find out what x, y, and z are. In this case, I found out y. Y is going to be negative 2. So I'll plug it in for what y would be. Again, I'm doing things by back substitution. So the only equation I haven't used so far is number 1. And if you look at equation number 1, you'll see 2x minus y plus 5z is equal to 24. I now know something about z. I know something about y. I have to know something about x. So I'm going to go to equation number 1. I'll say 2x minus y plus 5z is equal to 24. Now let's take and plug in what we know. We still don't know anything about x, so 2x minus, how about for y? We know y is negative 2, plus 5 times z. Z is 4, so I'll plug that in, and the whole thing is equal to 24. So now I have 2x Negative times negative 2 is positive 2. 5 times 4 is 20. So this will look something like this. I'll now reduce the left-hand side. I know 2 plus 20 is 22. So this will be 2x plus 22 is equal to 24. I'll subtract 22 from both sides. And I have 2x is equal to 2. I'll then divide both sides by 2. And I find out that x is equal to 1. So in this case, I have the last piece of my puzzle. I know that x is going to be 1. And I found everything by back substituting what I originally knew about z. So my final answer here would be this final answer that we have above, 1, negative 2, and positive 4. Since this shows up as a single point, what I can say is out of the 3 possibilities of what it could have been for solution, it's going to be this one here on the left, because I was able to find an x, y, and a z that matched up to what we were looking for. So in this case, our first example is complete. So not too bad. There will be a nice little progression here for the other examples we have to do. Okay, so feel free to pause the video if you want to take a look at the solution, or if anybody wants to talk about it, if you want to take a picture. You can also share the link with people if they want to watch it later, if they want to watch it again to try to get a better understanding, or to ask any questions or talk about it. Okay, so how about equation number 2? So I give myself 2 slides just in case I need extra space. I didn't need extra space for the first one, so how about example 2? Example 2 says, can we solve this following system algebraically? So again, kind of the same way. I'm going to start by numbering. I know that this will be my first one, this will be my second equation, and this will be my third one. So let's see if we could do it. So the first thing that I would try to highlight, and notice it's a little bit different than example 1, is try to find out which equation would be nice to kind of start with. Again, we have here, we're doing it algebraically, so we have substitution and elimination at our disposal. So the first thing that sticks out to me is equation number 3. I noticed that in equation number 3, it only has 2 variables, so I probably could solve for one of them pretty quickly. So I would start with equation number 3, and I would think to myself, would it be easier to solve for x, or would it be easier to solve for z? Which one would be easier to get by itself? So I actually think it's easier to get z by itself. So you can add z to both sides. So then you'll find out that z is equal to 3x. And if you want, you can throw a little box around it. Again, that's not our final answer for z because it's 3x. But the nice thing is that we might be able to substitute that into one of the other systems to try to find out what x or y or z is going to be. So like I did for the last one, I'll try to write my final answer up there on top so I don't eat up too much space down below. All right, so that would be my first step. The next thing that I notice is for equation 1 and equation 2, notice that I have x plus y plus z equals 6 for equation 1. I have 2x minus y plus z is equal to 3 for equation 2. And I notice something about the y's. I know that I have a positive y and I have a negative y. So for me, this would be screaming elimination. So just like I have it, I will write it x plus y plus z is equal to 6. And then for equation 2, I have 2x minus y plus z is equal to 3. I will add these 2 equations together, just like for elimination. If I have x plus 2x, this is 3x. I know y plus negative y are actually going to cancel out. They're going to eliminate. Z plus z is 2z. Just to not confuse you, my 2 is a regular 2, and then notice z has like a little line through it. And then 6 plus 3 is equal to 9. So now I know that 3x plus 2z is equal to 9. So the only issue with this equation, there are still 2 variables, and I don't know what x or z is. But what I do know from what I did earlier is that z is equal to 3x. So if I know that, I can now actually take that and plug it into here. So again, I still don't know anything about x, so I have 3x plus 2 times z. But I know z is the same thing as 3x. So then I can substitute 3x for z. So I have something like this. So then 3x plus 2 times 3x, well, 2 times 3x is 6x, is equal to 9. I know 3x plus 6x is 9x, and this is equal to 9. I can divide both sides by 9, and I have x is equal to 1. So that's kind of nice. That helps me out. So if I'm looking for a solution x, y, z, I now know what x is. It's going to be 1. And at the same time, I also know that z is equal to 3x. So I can take what I know about x equals 1, then I can put it back into here. So z would be equal to 3 times 1, because z is 3 times x, which is just 3. So in this case, I now know z as well. I now know it's going to be 3. So in terms of solutions, if we were looking for x, y, and z, you could say the only thing that I still need to find out is what y is. So in this case, we can try to go back to one of the other equations and now try to find out what y is. So then what I like to do is go back to the 3 equations and try to find out what's the simplest one to work with. And if you look at your options, I would say equation number 1. I think equation number 1 is a nice option to work with. So for equation 1, I have x plus y plus z is equal to 6. So I know that x is 1 and z is 3. So then I have 1 plus y plus z, which is 3, and the whole thing is equal to 6. I know 1 plus 3 is 4, so I have y plus 4 is equal to 6. Subtract 4 both sides. I know that y is equal to 2. So at that point, I have the solution to my system. It actually turns out to be 1, 2, 3. So I have x, I have y, I have z. So final answer for this guy, 1, 2, 3. Similar to the first one, you could say that this is the situation where we have one solution, x, y, z. So that'll be something good to know. Okay, so all right. Just like the first example, if people want more time with it, feel free to pause the video. If people want to stop the video and chat about it or take a picture, more than welcome to do so. All right, so that is example number 2. All right, we have one more example, and then the last example, example 4, and also example 5, I guess, talk about using the calculator in a matrix. Hopefully you guys are able to see a matrix before. I believe Mr. Irwin was supposed to show you something with matrix. So let's go to example 3. So example 3 looks something like this. It says solve the system algebraically. So let's see what happens. Let's see what kind of trouble we get into. So I would say this one, definitely a little bit different than the first two. So let's take a look. So first things first, I like to label my equations 1, 2, 3, just so I can reference them easily. And you guys will know which one I'm talking about. And notice how this one's different than the first two, is that we don't just have a variable that we know right away. We don't have an equation with just 2 variables instead of 3. Notice that all 3 equations have 3 variables. So this would probably mean that we probably should do some elimination, and we're probably going to have to do it more than once. Okay, so then let's start looking at options. So take a look at the equations. Do you notice that any of the equations are already set up for elimination? So maybe pause the video for a second. Would anybody be willing to say which equations could you work with that are already kind of set up for elimination? Well, how about equation 1 and equation 3? If you look at equation 1 and equation 3, equation 1 has a positive z, equation 3 has a negative z, so that would be a good thing in terms of elimination. So let's write it. Equation number 1, 2x plus 4y plus z is equal to 1. And then for number 3, I have x plus y minus z is equal to negative 1. So I'm going to do elimination with these. So I'm going to add them together. 2x plus x is 3x. 4y plus y is 5y. And z plus negative z cancels out. On the other side, we have 1 plus negative 1, which is 0. All right, so that's a good one to know. And if you want, you can put a box around it. We are going to use this one a little bit later. So if I put a box around it, maybe it'll be easy to reference. So we've done elimination one time, but notice it didn't help like greatly. We didn't just find out a solution right away, but it did help a little bit. We now have an equation with 2 variables instead of an equation with 3 variables. So now what we'll have to do is pick another 2 equations, try to work with them, and try to cancel out z's with elimination. So we can't use the combination of 1 and 3 again, but how about the combination of 1 and 2? It actually turns out that we could do those. So how about equation 1? This is 2x plus 4y plus z is equal to 1. How about equation 2? This is x minus 2y minus 3z is equal to 2. So then if I want to cancel the z's, notice that I can't cancel them right away. Positive z minus 3z is not going to cancel out. But what I could do is I could take equation number 1 and I could multiply everything by 3. So what we'll say is let's multiply this side by 3 and let's multiply the other side by 3. So if we do that, then equation number 1 is going to turn into 6x plus 12y plus 3z is equal to 3. Equation number 2 we're going to leave alone because we have negative 3z there, and that will cancel off nicely with this positive 3z. So we leave it as is, and let's do elimination. So let's start with the x's. 6x plus x is 7x. 12y minus 2y is 10y. And then we notice that positive 3z and negative 3z are going to cancel out. And if we add 3 plus 2, we have 5. So in this case, again, we didn't have a solution for one specific variable, but you can throw a box around it, and we can actually say that that's a good place to start. So now look at your two boxes. Notice that these two boxes both have two variables. They're both x and y. So we can actually use this to our advantage and just do regular substitution or elimination that we would have started with several days ago. So then take these two off to the side. So I'm going to take them and say, okay, here are my box questions, right? So I'll take this 3x plus 5y is equal to 0. And then right next to it, I have 7x plus 10y, and this is equal to 5. So what if I wanted to solve this? What could be a good method of doing it? Well, I like elimination, so I'm going to try it that way. But notice if I add these equations straight down, that they're not going to cancel, right? 3x plus 7x is 10x. 5y plus 10y is 15y. But the y's are actually looking pretty promising. On the bottom, I have 10y. So on the top, if I could somehow get negative 10y, then they could actually cancel out. So what we can do is we can take the first equation and we can multiply everything by negative 2. So negative 2 times 3x is negative 6x. Negative 2 times 5y is negative 10y. And then negative 2 times 0 is going to be 0. The second equation I'm going to leave alone. 7x plus 10y is equal to 5. Again, the reason I'm leaving it alone is because that positive 10y in the second equation is going to cancel out nicely with that negative 10y in the first equation. So now if I add these guys together, negative 6x plus 7x is 1x. Negative 10y cancels out nicely with positive 10y. And 0 plus 5 is equal to 5. So the nice thing there is now we have x. So if we're building our solution on the top here like we did for the last ones, I now know that x is going to be 5. All right, so then what's next? Well, if I know what x is, I have to find out y. So then maybe take a second. Where could I take x equals 5 to try to find out what y is? Well, I couldn't plug them back into the original equations because notice the original equations have x's, y's, and z's. So if I plugged it back there, I would still have two variables. It wouldn't be extremely helpful. But what if I plugged it back into one of these two boxes that I have? So what about for this one right here? So I have 3x plus 5y is 0. Well, 3 times x, what do I know about x? Well, I know x is now 5. Plus 5y is equal to 0. So 3 times 5 is 15. Plus 5y is equal to 0. I can subtract 15 from both sides. So 5y is equal to negative 15. I can divide both sides by 5. And if you divide both sides by 5, you'll find out that y is equal to negative 3. So now we have x and we have y. If we go up top, we can drop in negative 3 for the y. So the last thing we'd have to find out is z. So for this, we actually could go back to one of the original equations. Notice those have x's, y's, and z's. We now know something about x and y. So if we take these two values of x and y, we plug them into one of the original equations, we could actually solve for z. So I would think to myself, what's the easiest equation that I can work with up there? And I choose equation number 1. I think 1 is the easiest because it has everything that's positive. 2x plus 4y plus z is equal to 1. So let's plug in what we know. For x we know is 5, so 2 times 5, plus 4 times y. Y we know is negative 3. And then plus z, which is still the only unknown. And the whole thing is equal to 1. So let's start simplifying. 2 times 5 is 10. 4 times negative 3 is negative 12. Plus z is equal to 1. We know that 10 minus 12 is negative 2. So I have z minus 2 is equal to 1. I can then add 2 to both sides. And you'll find out that z is equal to 3. So in that case, I can go up top. I can drop it in for what I know. And I could say my final answer here is going to be 5, negative 3, and then positive 3. So I would say this one is an example of one that maybe requires more work because we don't just have one of the variables by themselves right away, or we don't just have an equation with two variables right away. So you gotta have to mess around with it a little bit. I will tell you that sometimes the first thing that you do won't always help you get to a solution. But don't give up. Try a couple things, right? I'm not going to assign you, 100 problems that are like these. I might only assign you a couple because I really want you to take the time to try it. And if something doesn't work right away, then maybe you try something different and see if you can come up to the solution. Okay, the last two examples that we have in the notes talk about doing things with a matrix. So hopefully Mr. Irwin got a chance to show you guys the matrix. I think some of you guys, I would have shown the matrix before in a previous class. So what about this one right here? So first start off with how many equations? Well, I have 3 equations, right? So that's not much difference. Let's see if we can solve this with the matrix. And inside of a matrix, we have to talk about the size of the matrix. So the size of the matrix is always going to be the rows by the columns. So how many rows do we have? Or how many equations do we have? We have 3 of them, times how many columns? Well, this would be column 1, this would be column 2, column 3, column 4. So this is a 3 by 4 matrix. So we got to take this into the calculator, and we're going to have to plug in these values that we have here. So maybe the first thing we can do is write it kind of like a matrix. So let's steal some coefficients. What's the coefficient of x in equation 1? Well, it's a 1, so then we'll start with the 1 there. The coefficient of y is going to be -3. The coefficient of z is going to be +1, and then is equal to +1. How about in equation 2? Well, I've got 2, I've got -1, I've got -2, I got +2, and then I've got 1, I've got 2, I've got -3, and I've got -1. So again, this is your 3 by 4 matrix that we're going to plug into the calculator. So I'll kind of do it verbally in case you forgot. You could hit second on your calculator, so pick up your calculator, hit second, and then x to the -1st. If you look right above the x to the -1st button, you'll see that there's the word matrix. Go over to edit. On letter A, go ahead and press enter, and then go ahead and make it a 3 by 4. So put 3, enter, and then put 4, enter, and then plug in all your numbers. So let's plug in the 1, -3, 1, 1, and then 2, -1, -2, 2. On the bottom row, 1, 2, -3, -1. Now we need to back out of it. So go ahead and hit second and then mode. When you hit second mode, it will quit, get you back to the home screen. Then go back to where we started. Hit second, x to the -1st. Scroll over once to the right to the math column, and then go ahead and scroll up. When you scroll up, we're looking for RREF, which stands for Reduced Row Echelon Form. On my calculator, it's the letter B. Notice it has 2 R's and then EF. Right above it, it has a single REF, but we want the double R, RREF. So go ahead and press enter. When you do that on your home screen, you'll now see RREF and a parenthesis. So then one more time, hit second, x to the -1st. Under names, go ahead and press enter on letter A. And then on your home screen now, it should say RREF parenthesis and then A in brackets. Go ahead and press enter. When you press enter, I'm hoping that you see a matrix that looks like this. So, kind of going down the line, we know that the first column was x's. So if we go here, the first place in the first column where we see a 1 is the first guy. And if we look at the second column, you'll see that there are y's, where we see the y there. So then this will kind of be corresponding to x here. The second column kind of corresponds to y. But then if you go to the third column where z is supposed to be, notice that nowhere in the third column do you see a z. And the last row has zeros and it has 1s in it. So in this case, this actually means that there is no solution for z, which means there is no solution for this matrix. So this would be something to note down in your notes, is that if you have any rows that have zeros and it's equal to a 1, or has a 1 there and zeros, that this actually means no solution. So if we go back to the original picture that I showed you about 3 variable systems, this would be like saying that these 3 planes don't have any intersections in common. These 3 planes don't intersect each other, so they don't have any solutions. So let's do one more. So how about example number 5? Example number 5, let's go ahead and jump into it. So we get something like this. Notice that we still have 3 equations. We're going to try to do this one with a matrix as well. So let's just go down the line. We know that there are 3 rows, so there's a 3-row matrix. It still has 1, 2, 3, 4 columns, so it is a 3 by 4 matrix. what would it look like into the calculator? Well, let's steal some coefficients. The coefficients I can see on top are 1, and then 1, -3, and -1. For equation 2, notice there are no x's, so that means for the x term that would actually be 0. For positive y we have a 1, and for z we have -1. We know that it's all equal to 0. On the last equation we have -1 for x, we have +2 for y. Notice the z's are missing, so that means for z you would be 0, and then +1 there at the end. Okay, so it's still a 3x4 matrix. I'll give you a second, maybe pause the video. Could you go back into the calculator, make a matrix with these coefficients, and then solve it using the RREF program? So go ahead and pause the video so everybody can do that. And once you have it, go ahead and press play. All right, hopefully you got a chance to try it. So in this case, this is what should have come back to you there at the end. So if you do this one, you'll notice that the first column's got x's. So this is where x would be. The second column is y's, so you have it there. And then for the third one, you're supposed to have z's. But if you look at it, you'll see that there's nothing there. But we do have an entire row of zeros. So an entire row of zeros is actually a good thing. So if you wanted to, you can write it down in your notes. This actually means that there are infinitely many solutions. So in this case, it's not no solutions. Notice there are no ones in this last row. So in this case, we have all zeros. So this would mean that there are actually infinitely many solutions. This would mean that these three planes actually intersect on a line. And the line goes on forever. So that's why there will be infinitely many solutions. So from the calculator, there actually is a difference when you have a row with all zeros versus a row with 0 and 1. A row with 0 and 1 is no solution, where a row of all zeros is infinitely many. If you want to see something interesting happen, go ahead and solve one of those ones that we did on the front side, maybe example 3. If you try to solve example 3 using the same method that we just did, it will actually show up in your calculator with 1s and 0s. So maybe I'll show you what this one would look like. So if you want, you could do another 3x4 matrix using these coefficients that you have here. And then if you go into the calculator, we had a solution of 5, -3, and 3. So 5, -3, and 3. If you actually run this one through your calculator, what you'll actually see the calculator give you back will be a 1, 0, 0, 5. Then it'll be a 0, 1, 0, -3. And then a 0, 0, 1, and then a +3. So then this first row, or first column, corresponds with this first column. So this is where x would be. So this would mean that x, if you scroll all the way across, will be equal to 5. If you look at the second column, you'll see that there's a 1 here. This would correspond to y. And if you go all the way across, you'll see that y is -3. In the last column, you have z's. So if you look at the 1 here, you'll see that this is going to be z. And if you scroll all the way across, you'll see z is equal to 3. So this would be the case on the calculator where you see one solution. So we know that if we got something like this, this would be one solution on the calculator. If we got a final row with zeros and ones, then that would be no solution. And if we got a final row with all zeros, then that would be infinitely many solutions. Sorry, Watson is trying to get my attention, so this is all the noise that you're hearing in the back. He's trying to jump up on the desk and trying to get my attention. So I am trying to pet him at the same time that I'm trying to make the video. Okay, so again, example 4, you see that row with zeros and ones, so no solution. In example 5, you saw the row there at the end with all zeros. This would be infinitely many solutions. Okay, so feel free to pause the video and chat about it. Otherwise, the assignment for today are just those 2 other questions that are hanging out there. And we do have access to some solutions. So if you wanted to try them and then take a look and see if you got the solutions right, then that would be great. I am asking you to try the questions by hand, and then you can use the calculator to double check your answers. So feel free to work together, chat about it. If you don't finish it in class, it'll become the assignment for the weekend. So hopefully the video was helpful, guys. Try working together and see if you can figure it out. It's actually not that bad, and you do have the matrix to help double check. All right, guys. Have a good rest of your day. See you next time.